Kristin, what's up?
Well, Karen gave me the sample and told me to characterize it.
Okay, do you know what it is?
Yeah, it's powder.
Oh, but what kind of chemical?
That's a really good question.
Let's take a look. Does it happen to be calcium oxalate?
Maybe it is.
Okay, well we can still characterize it using thermogravimetric analysis with mass spectrometry.
That sounds really fancy.
Well, fortunately, here at Texas A&M University at the soft matter facility, we have one. So let's go. So this instrument right here is called the TGA, which stands for thermogravimetric analysis. Here at the soft matter facility, we utilize the TGA which is their higher end type of TGA. In this specific instrument, we have a built-in user interface. However, I find that the TRIOS program on a computer is much easier to use, in my opinion. Now, there are different add-ons that we have with this system, such as the gas blender, which helps us blend different gases such as CO2, nitrogen, oxygen, and so that can help us use different experimental situations. We also have an auto-sampler here, which enables us to queue many different samples. And then lastly, our mass spectrometer, way over there, that helps us analyze the composition of different evolved gases.
Wow, so TGA is pretty versatile then.
You bet. The TGA utilizes many different types of pans. It all depends on your sample's reactivity and the temperature range of your experiment. Here we have the three most common types of pans used. Starting with the lowest temperature to the highest temperature. The lowest temperature is the platinum pan, and then we have a platinum high temperature pan with a ceramic coating at the handle, and lastly the ceramic aluminum pan.
Well, what happens if your sample reacts with platinum?
That's a great question. Then you should utilize the ceramic pan, because that usually is less reactive for most situations. But in our case, with the calcium oxalate, we can just utilize the platinum high temperature pan. We have to get the instrument ready for mass spec.
What does that entail?
Well, it depends on the instrument.
So what would we do for the TGA 5500?
So this specific mass spec unit utilizes a software called Process High Professional, and that basically controls the parameter of the mass spec, as well as the temperature of the capillary tube and when it starts and finishes collecting data. In this specific instrument, we utilize a heavily insulated capillary tube, and this has a lid tubing on the exterior to prevent condensation of evolved gases from the sample. The diameter of the capillary tube also dictates the sensitivity of the mass spec units, with a thicker diameter having higher sensitivity. Now, before we can actually insert the capillary tube into the furnace, we have to clean it out. So we utilize a process that just runs the furnace up to 1000 Celsius for a given amount of time until the unit is nice and clean. After that, we could start increasing the temperature for the capillary tube as well as the evolved gas port.
After the furnace has been properly cleaned, the student could then carefully put the capillary tube into the evolved gas port, careful to not bend the capillary tube.
So now we can load our sample, right?
Not quite. It's always good practice to clean your TGA pan, and so we utilize a flame torch until it's bright red, like so. Make sure you don't bend the platinum because it is soft. And then after it's cooled, you can tear it.
Most TGAs use a platinum hook. Don't touch it, because it can easily bend and ruin the data. This TGA utilizes an auto-sampler. However, most instruments will have an automated loading feature to avoid damaging the hook by manually loading the sample. When the sample pan is loaded, be sure to verify that the pan is not on the tip of the hook and that the pan is level.
Now can we load the sample?
Yes. In this case, just put enough sample to cover the bottom of the pan. Approximately 5 to 10 milligrams would be the trick.
The student will then load the filled sample pan onto the auto-sampler. And just like with the tearing process, the autosampler will then load the sample pan onto the hook, as such. Okay, now that our TGA experiment is over, we can analyze the data. We will have two files, the TGA data shown here and the mass spectrometry data shown here. As you can see, the mass spectrometry data isn't that useful at the moment. And we would like to have both the TGA data and the mass spectrometry data on the same graph. So to do that, we will highlight both of the data sets, right-click, go to Transformations, and say Add TGA temperature data. This will bring up a new graph. Now we will add in the TGA data by clicking on it and dragging over to the graph to give us a file overlay. It's not shown right here because there's no axes that is labeled with any of the information that it has. So we will double click on the ion current axis, go to Y2, and add the weight percent. You can also do weight in milligrams as well. On the x-axis, we will change it from time to temperature. We'll press OK. And now we'll see that the TGA data is overlaid onto the mass spectrometry data. Now still the mass spec data is not that useful at the moment, so we'll change the scaling of it. We'll go to log base 10, switch over the scaling to manual, and go to 1e to the negative 4. Apply and press OK. So great, so now we could see some general trends. However, there's a lot of data points, so it's kind of hard to see anything going on here. So we'll go and highlight the file overlay data set, and we'll go down to Transformations and click on Reduce. I usually do between 10 and 20. In this case, we'll try 15. Perfect. So there's a lot less mess going on with the data points, so we could see more of a general trend that is occurring. So if we look up calcium oxalate and kind of understand the decomposition routes for each mass loss event, we'll have a general understanding about what we're going to expect to see. So for example, this first mass loss event should be just water. So if we start clicking on some of the peaks that have peak right here, we'll see that water with a mass of about 18 will have peaks that are around 18. The second peak should have carbon dioxide and carbon monoxide. Unfortunately, with carbon monoxide, since it's carbon and a oxygen atom, it's going to have an AMU of 28. But our feed gas was nitrogen, and nitrogen, which is diatomic, so 2 nitrogens, has an AMU also at 28. So we're not going to see much change for carbon monoxide. Lastly, the last 2 peaks will have carbon dioxide. And so carbon dioxide has AMU of about 44. And so we expect to see peaks at around 44. Okay, so if you can see the circled points increases, they keep increasing as we go from the second mass loss event to the third mass loss event. Additionally, you can export the TGA-mass spec data into a plain text or an Excel document. Here is an example of what the data exported to Excel looks like with the mass spectrometry data. So it gives you the different sheets, each corresponding to a specific AMU. And here we have 2 columns, one for the time and one for the ion current. So you could gather your specific AMUs that you want to graph and put them on another Excel spreadsheet to graph them like so. So as you can see, we see that the 28 AMU corresponding to nitrogen and carbon monoxide shows up here, because again, there's going to be a lot of it since that is the feed gas. Zooming down by removing that 28 AMU, you can see that there's more going on over here. So for example, we over this green area, that is the 44 AMU corresponding to the carbon dioxide. And we also have the good old 18 AMU corresponding to the water. And of course, a little bit right here too, with the 17 AMU also being present. And then of course you get 14 AMU corresponding to that nitrogen as well, or carbon monoxide.
What if you have a sample that's a mixture of polymers?
This is a good question. So it becomes a problem when the thermal degradation temperatures are the same for the different types of polymers. So that might cause overlapping and really convolute your mass spectrometry data. And it's highly recommended to use different types of techniques, such as gas chromatography or size exclusion chromatography, to help supplement this data further.
Help today. I think Karen's really gonna like this data.
No problem. I'm glad I could help out. Remember, instruments may vary, so consult your lab technician or your manual. Further information about the TGA can be found in the description below. I'm Cameron Taylor.
And I'm Kristin McCormick.
And we're from the PenCert group here at Texas A&M University. Thanks, and gig 'em.